Hi, my name is Christoph Meyer. I'm a PhD student at ETH Zurich, and I'll present our paper, Learning Target Association to Keep Track of What Not to Track. This work was done in collaboration with Martin Dannelian, Danda Poni-Podel, and Luc van Gool. Generic object tracking is the task of localizing any given object in every frame of a video. Most of the state-of-the-art trackers, such as Siamese or discriminative correlation filter-based trackers, primarily do appearance matching. These trackers produce a score map where regions achieve a higher score if they are visually similar to the target. One of the main open challenges in tracking is handling distractor objects. Distractor objects in the scene that are visually similar or even indistinguishable to the target and achieve high values in the score map. Distractor objects often cause tracking failure if the distractor achieves a higher score than the target. The tracker then continues to track a distractor instead of the target. In practice, distractors are very common because objects of similar appearance often co-occur. In this work, we propose to not only keep track of the target, but also of distractors. From the appearance-based tracker, we use the score map to detect target candidates. The set of target candidates contains the target and the distractor objects. Hence, the tracking problem translates to selecting the target object from the set of candidates. To solve this problem, we propose to use the previous frame and its target prediction. Our idea is to match a previously predicted target in order to select the best fitting candidate. In addition, we propose to not only match the target with the candidates, but also the previously detected distractor objects. By matching distractors, we eliminate potential matches for the target object and simplify the problem of selecting the candidate that corresponds to the target. In order to predict the assignment of candidates between frames, we extract a set of features, such as the score values, visual appearance features, and the location of each target candidate in the previous and current frame. After extracting the features, we encode them into a single feature vector. Then we enhance these features using a graph neural network consisting of self and cross-aggregation layers. This enables the exchange of information between candidates in the same or in neighboring frames. And finally, we feed these refined features to the optimal matching module that predicts the assignment probabilities of all candidates across frames. To train the proposed association network, we require annotations for target and distractor objects. However, most generic object tracking datasets provide only a single annotation of the target object. Hence, we can use these annotations only for partial supervision of our model. Namely, we supervise only the association of the target object between frames. In addition, we make use of self-supervision to learn distractor associations. We enable this by synthetically creating the features of the previous frame by augmenting all the extracted features from the current frame. In this scenario, the assignment between the distractors across frames is known and allows full supervision during training. During inference, we keep track of distractor objects over the full sequence by assigning a unique object ID to each detected object. Then we use the predicted assignment probabilities to propagate these IDs from frame to frame. This directly enables matching the target and distractor objects between frames. In addition, we assign a new ID to each object that does not match with any object in the previous frame. Our tracker is able to match distractors and the target object across frames. Our tracker keep track is robust to distractors and keeps tracking the target object instead of following a distractor even in cluttered scenes, or if the target undergoes partial or full occlusion, or if strong distractors appear. When comparing keep track with the baseline tracker SuperDim, we observe that keep track gets less confused by distractors and keeps tracking the target for cases where SuperDim fails. Keep track achieves new state-of-the-art results in 6 benchmarks. In particular, it achieves 67.1 AUC on LaSOT and almost 70% on UAV. Moreover, keep track outperforms recent trackers on the long-term datasets OXUVA-LT and VOLT-LT19. Thank you for watching, and don't forget to check out our GitHub repository with PyTorch code for our results and trained models.